So the second talk is Giant Does Not Mean Strong, Cryptanalysis of BQTRU by Adi Raya, Vikas Kumar, Aditi Gangopadhyay, and Sugatas Gangopadhyay. And the talk will be given by Adi.
Thank you for the introduction. So yeah, this is Ali Raya, and I am presenting our work titled Giant Doesn't Mean Strong, Cryptanalysis of BQTRU. And this is joint work with my colleague Vikas Kumar, Professor Aditi, and Professor Sugata Gangopadhyay from IIT Roorkee. So first of all, we'll give a small context about intro before describing the BQTRU scheme which we are attacking. Intro actually as one of the extensively studied lattice-based crypto system, almost received a lot of crypto analysis. 3 decades of crypto analysis couldn't underestimate the trust in intro assumption. And because of the freedom of design of building intro variant, we had many schemes in literatures which is intro-like crypto systems based on commutative and non-commutative rings. If we want to formulate the problem in simple word, as it was introduced in the first proposal of intro, that is constructed over the truncated polynomial ring. Basically, we are sampling 2 elements, f and g, from the underlying ring with a small coefficient. One of them is invertible, f, and then we are calculating the public key h as a f inverse g. And in this context, the search problem of intro is asking you to find these 2 short elements, f and g, giving h. There are different ways to attack this problem, different passes to tackle this problem. One of them is to search. This is a naive way to search for this element from the ring that satisfy intro equation. Other ways is to build a lattice where this short vector lie, and you try to reduce the lattice in order to find the short vector. And the structure of the lattice is heavily depending on the underlying ring where we are constructing intro. Other kind of attack against this problem is combined attack, which try to combine the search technique with the lattice reduction, like the hybrid attack. And there are also other attacks that is exploiting the parameter selection. So in this context, whenever we want to select a parameter that satisfies certain level of security for intro, we will consider the best attack that against our construction, and based on that, we will define the parameters that achieve the required level of security. Till now, the lattice-related attacks, or the combined with lattice reduction attack, they are the most successful attack against intro constructions. And the cost of the reduction is basically a function of the dimension of the lattice, and also the norm of the short vector, which we are looking for with respect to the expected one, or what we call the lattice gap. So other attack, like gentry attack, which we are extending in this work to different algebra, they are exploiting the structure of the ring. For instance, the gentry attack, which was proposed against the proposal of intro, the initial proposal of intro, which was trying to support faster multiplication, tried to define a homomorphism that can send the short vector that lie in the original lattice to lattices of a smaller dimension, and therefore made the lattice reduction much easier in retrieving images of the short vector and pulling them back to the original lattice. So in this work, what we are doing, we are extending gentry attack to other non-commutative variant of intro. Why non-commutative intro? Actually, in our effort to develop a non-commutative intro-like construction, since we have found that there are some attacks that can be avoided by if we are implementing or constructing a non-commutative variant of intro, namely intro learning problem, which was believed to be hard. It has recently a polynomial time attack which can retrieve the key. And when we analyze this attack, we found that commutativity play a role in retrieving the key of the relaxed problem of intro, or what's called intro learning problem. So in our effort to build non-commutative variant of intro, we found always that this non-commutative variant, they are coming to be slower in real time or implementations. However, BQTRU, which was published in Design Code and Cryptography 2017, it was an interesting proposal since it is a non-commutative analog of intro first of all. And second, it's claimed to be more than 2 times faster than intro when it's come to the key generation and encryption at least. So in this work, we are showing that one can extend gentry attack to the underlying algebra of BQTRU, and hence we can provide efficient key and message recovery attack, and we are providing implementation for the scheme and the attack against it. Yeah, so let's give just a small introduction about the scheme, how it's work, so that you can be familiar with it. Then we can introduce the attack. So the construction of BQTRU is based on quaternion algebra, which is considered in the paper, that can be considered as a 4-dimensional vector space with respect to the bases 1, I, J, and K. And we are selecting 2 elements, A and B, from the underlying field that is defining the multiplication rules. Also, one can define the quaternion with respect to commutative ring with unity instead of the field. And the author of the paper, they have selected the commutative ring ZXY over quotient by x over n minus 1, y over n minus 1. Also, in the parameter selection, they are taking a condition where n is always dividing q minus 1 so that they can represent any vector with respect to Lagrange bases in addition to the monomial bases. So simply speaking, that any element which is sampled from this ring, we can look to it as a vector of dimension 4n square. And in order to represent this element, we have 2 options. The first one is to do the usual or straightforward embedding by taking each coefficient from the original vector to the corresponding vector. And then, therefore, since we are working over quaternion algebra, we will be having 4 copies of this vector. This is the straightforward representation. The other one is to represent any vector with respect to Lagrange bases, as we mentioned. Then here, each coefficient will be the evaluation of the function, but with respect to the Lagrange bases. And since we are working over quaternion again, we will be having 4 copies of that as a vector. So in BQTRU, the idea which the author claimed that it make the key recovery attack much harder, that they were modifying the key generation of intro by masking the key with an element coming from the private ideal. And how did they define the private ideal here? They were taking T bases from the Lagrange bases and considering all the integer linear combination of these bases. So we sample an element from the private ideal, and then we mask our key with the element which is sampled from this private ideal. For sure, we have a way to generate the lattice that is generating the private ideals and over also the quaternion as well. So in simple word, the key generation of BQTRU is pretty simple to intro variant. And here we can see that we are masking, the public key of intro that is f inverse g with an element v that is coming from the private ideal. So this is the proposal, the original proposal. And intuitively, it may look that it's harder than intro problem, since one need at least to guess v, that is the private element, which is coming from the private ideal, before going further and solving intro problem. However, in this paper, we are showing that the selected algebra doesn't make the problem harder. On the contrary, it's easier to attack. Why? Encryption is pretty similar to intro, exactly the same equation. And for decryption, there is little bit some trick that one needs to solve CVP before going further so that he can remove the effect of the private ideal and then he can retrieve the message as in the original intro. Solving CVP is not possible, but here, because of selecting quaternion algebra, instead of solving the CVP with respect to the original lattice, one can decompose this problem into 4 smaller versions, and that's why the decryption is possible when it comes to BQTRU. So in simple words, the BQTRU problem here, if you want to compare it to the intro one, you are giving the public key H, and you are asked to find 3 elements, F prime, G prime, and B prime, where F prime, G prime, they are short in the Euclidean norm, and V prime, which is coming from the private ideal, is small in the Hamming weight and not in the Euclidean norm. And totally, the entire vector, F prime, G prime, V prime, will be short in what's so-called the hybrid norm. That is the combination of the Euclidean norm and the Hamming weight. And because of that, the author, they are concluding that this vector, the private vector which we are looking for, lie in a lattice, but it's not short in the Euclidean norm because V is not short in the Euclidean norm, and therefore one cannot apply lattice reduction algorithm directly like BKZ to retrieve the private key. And in order to apply lattice attack, one needs to expand the lattice so that he can transfer this vector to be short vector in the Euclidean norm only. And hence, this scheme, by and large, according to the author, can avoid lattice attack, which is mainly the most successful attack against intro-like construction, because we are resulting in solving the lattice reduction algorithm in giant lattices of very large dimension. So we can consider this lattice of a very giant dimension in the case of BQTRU. So in our case, what we did in order to attack this problem, first of all, we try two-step attack. The first step is to guess the element which is sampled from the private ideal. And because of the way of selecting the parameter of BQTRU, one can see that the G, that is the private element, when you represent this with respect to Lagrange bases, instead of having our multiplication between F inverse and G, here can be transferred into coefficient-wise multiplication and addition when you are representing your element with respect to the Lagrange bases. And in this case, if we are able to guess only the position of the Lagrange bases that generate the private ideal, by doing evaluation for the public key H, we will be able to retrieve the coefficient evaluated with respect to Lagrange bases for V, and therefore we will be able to retrieve entirely the private element V, which is coming from the private ideal. So upon successful retrieving of V, one will be able to transfer this problem into a problem that is exactly similar to the intro reduction, and we will be able just looking for a short vector F and G that lie in purely Euclidean lattice instead of the hybrid lattice that has been proposed in this work. So first of all, after guessing correctly the element, which is coming from the private ideal, we can convert this problem into a similar problem to intro and just look for a vector F prime, G prime that lies in a purely Euclidean lattice. So at this stage, it is as hard as intro problem at the same dimension after guessing. All right. What happened? Okay. Yeah. Fine. Time is over? No, okay. Should I continue? Or? Okay. Okay. Yeah. So at this stage, it's as hard as intro problem for this dimension. Furthermore, if we check the structure of the quaternion, where BQTRU is built, the matrix corresponding to the quaternion algebra here, it have very nice symmetry, and therefore actually one can define a homomorphism that sends the short vector that lie in the original lattice to short vector that lie in lattices with half the dimension. And this is similar to the idea of Gentry, but in the case of Gentry, he was decomposing the algebra into a smaller algebraic ring. Here we are just working from the perspective of matrices. So in this regard, one can solve the lattice reduction in lattices of half the dimension of the original lattice, and the norm of the vector which we are looking for is as long as the original vector. That's why the problem is not harder, it's much easier. So for that, if we want to easily summarize the key recovery attack, first of all, we are guessing the element V, which is coming from the private ideal. then we will be ending up with purely Euclidean lattices and the case of intro. Here we are looking, there is a vector that is short in the Euclidean norm lies here. Then after that, we can apply homomorphism that is further reducing the dimension of the original lattice. And we are looking for the image of the short vector in the dimension reduced lattices, which is easier to tackle by lattice reduction algorithm like BQC. Then we can lift back or pull back the solution to the original Euclidean lattice. So here we will be ending up with reducing a lattice of dimension 4n square compared to the original giant lattice which the author proposed, and the attack is becoming much easier since the dimension is further reduced. The message recovery attack is similar and straightforward because the equation of the encryption is similar to intro. So here we don't need to guess, we just need to apply the homomorphism directly. First of all, we are converting the CVV problem, which in the encryption using canon embedding to the SVB. And then we are applying our homomorphism, solving the lattice reduction in half of the dimension of the original lattice and pulling back the solution to the original lattice. And depending on that, if you want to revise the security, for instance, the dashed line, the red one is referring to the estimation of the key security according to the paper, and the continual red line is our estimation. For instance, for the parameter n equal to 7 in the original paper, the security is estimated to be more than 2 to the power 166. However, according to the new proposed attack, it's less than 2 to the power 50, which can be practically retrieved. Also here, we can see that our experiment actually matched the security estimation. The red cross here refers to the block size, beta, that is required to retrieve the key in the case of applying our homomorphism and the attack. And as you can see, the red line is a little bit higher than the cross, the red cross, because the key attack include guessing part with addition to the guessing part with addition to the lattice reduction. However, in the case of the message attack, you can see that the crosses are matching the line because the message recovery attack is purely related to the lattice reduction. Yeah, so in this way, we can see that for sure, when you are reducing the dimension to half of the original dimension, here we can see in the column folding, we are reporting the block size needed to retrieve the key after applying the homomorphism. And the case of no folding, that is the block size without applying the homomorphism. For instance, for the beta message for the toy example n equal to 5, you need a block size 56 to retrieve the message without applying the homomorphism, while after applying the homomorphism, you need a block size almost 7. And in the case of the parameter set with n equal to 7, you cannot experimentally verify because the block size is larger than 100. However, here we can retrieve the message with block size 63. And as you can see, always the block size that is needed to retrieve the key is smaller than the one needed to retrieve the messages of similar dimension, because when it's come to the lattice that is contain the key, we have also the rotations of the key lie in this lattice, and this effect of rotation help in getting smaller block size to get the key. And similarly, the estimator, the theoretical estimator of the block size, they are also following that after applying the homomorphism, you need smaller block size compared to the original technique of reducing the lattice. As a conclusion, we want to say that giant doesn't mean strong, but could be. And this is will be an interesting work, the idea of building a scheme based on hybrid lattices. In our opinion, it's an interesting proposal. If someone can avoid building the scheme over a very over-structured case like the one which has been proposed here, but then we will face the problem of, for instance, if we want to follow the same logic here, how to decrypt. because here decryption need apply CVP, and the idea of introducing quaternion what is smart enough in order to enable solving CVP by breaking down the problem into 4 smaller dimensional lattices to make the decryption possible. So our future work may include designing a scheme based on hybrid lattices where one can avoid the structure and enabling the decryption, maybe by designing some trapdoor. Thank you.
We have time for a few questions. Can you come back to the slide explaining the BQTRU crypto system?
This one?
The one explaining that, so for the key generation, you need to solve a lattice problem in smaller dimension, right?
In decryption, yeah. Here. Yeah.
But the lattice security with respect to the high, what is the dimension of the big lattice for which
for instance, for the first param n equal to 7, the dimension of the lattice is, here the vector is 4n square, means for n equal to 7, it will be 49 multiplied by 4. This is the dimension where you want to solve CVP. Originally, it will be hard, but when you break it down using quaternion, you need to solve CVP in 49 dimension. And this is because you are building over quaternion, you can do that.
But so are you saying that the lattice dimension that you need to solve is a fraction of the initial underlying lattice?
Yeah, when it's come to decryption.
But then asymptotically, this is still very hard. I mean, if you take a fraction, so how is it practical? I don't.
Yeah, I mean, the author, they are they are solving the CVP on this parameter that they have proposed. For instance, here in dimension 49. And their claim is for encryption that key generation, it's faster. Decryption is practical, but sometimes it's a little bit slower.
And the same for the Gentry attack. Initially, the problem is you may have reduced the dimension, but yeah, it's not necessarily an easier lattice problem. It depends about the density. So how do you know, what is the intuition behind the fact that the new lattice is easier, and not just in terms of rank?
Yeah. The new, if you look to the defined homomorphism, just like, let's see. Here. I mean, when we are defining our, for instance, your short vector is ternary vector. So you can divide the vector into 4 sections, F0, F1, F2, F3, that lie in the original lattice. And then the image of this vector is the folding of the original vector. So if the original vector was ternary, the image will have at most 2s or minus 2s. And experimentally, the norm of the image of the vector is almost equal to the norm of the original vector that lie in the original lattice. So in this case, we are here searching for a vector in half of the dimension, which is also having the same norm.
But this is the absolute norm. What about the covolume of this new lattice?
The volume of it's also a query lattice, this one. So the volume, just 1 minute. Yeah, so it is Q to the power 4n square. Here, whatever we are looking for, and the norm is almost same as the original one. For the original lattice, the norm is same, and the volume of the lattice is Q to the power 8n square. So here, this is the reduced one. You are looking for a vector in the same norm, and the volume is Q to the power 2n square, sorry. And in the original one, the volume is Q to the power 4n square. So the lattice gap will be here easier to attack when you consider both the dimension and the volume together.
Okay, thanks for the clarification. Is there any other question? Yes.
So thank you for your presentation. So you proposed 2 attacks, yes? So which attack is dominant? Dominant attack which?
You mean which attack is dominant against this variant?
The parameters for the parameters. So you revise the parameters.
Yeah.
Yeah. So which attack depends on the
actually,
parameters?
the attack which is dominant in our revising the security of the parameter is a combination. It's kind of hybrid attack. First of all, you are guessing some values in the which enable you to retrieve the private IDL. Then you are doing lattice reduction. So it's a combination of guessing and doing lattice reduction, both.
Okay, thank you.
Yeah.
Any other questions? Okay, so let's thank the speaker again.
Thank you.